Okay, for project 6, we're going to look at generating text with recurrent networks. Can networks learn to generate interesting text? So we're going to start with importing our standard libraries, and then there are 5 tasks you're going to look at, and they're somewhat tied together. The first one is we're going to look at character input in a long short-term network. And then we're going to modify that character-based network in the second task. Then in the third task, we're going to look at word input in the long short-term network and then modifying that. And then we're going to have you do a little research into encoder-decoder networks, which are been shown to really improve this sort of performance and are kind of the cutting edge networks for this sort of work. So let's look at character-based inputs here. So you're gonna have be able to choose between 3 texts: Alice in Wonderland, Wonderful Wizard of Oz, or the King James Bible. They're different sizes. So the first one's 140,000 characters, and 220,000 characters, and then 4 million characters here. So you do have to watch the number of epochs in the training, depending on which one you feed in. If you do choose to choose the Bible, it's a huge text, and you won't be able to train it in as many epochs here. Okay, so here's where you would set up your data here. So we've got our 3 URLs to our data stored on GitHub, and then you select which one you want. So URL Wonderland or Bible or the Wizard of Oz. So by default, we're just going to do the shortest one, Alice in Wonderland. So we're setting up that URL, we're opening it and reading up the text. And here's the first text: down the rabbit hole, Alice was beginning. So that's our start here. So we're going to read that in. And start sorting the sequences out here. And again, this is the number of characters, and this is the vocab, the number of different characters. We're switching this all to lowercase characters up here. And you would think, oh, there just should be 26 characters then, but we have a lot of special characters. We have single quotes and punctuation marks and things like that, including the space here. So it turns out not 26, but 42 characters we have in our input. Now we use this method that's going to convert this into training sequences. We're going to feed it in sequences of 100 characters and have it predict the next character for this. So to give an idea of what's happening here is we are taking each character, each letter, and converting it into a number, and we're going to feed those numbers into our network. And our network only sees one number or one character at a time through this. So we're going to see one character at a time as we go through this. Here's an idea of what the network will see. So again, this is the challenge. It's just seeing one letter at a time. So it's seeing the A, L. So it's seeing this, and it's trying to figure out what the next character will be. And again, even for us humans, seeing that one character at a time is harder. Where if we were to see the whole sequence here, that would be a lot easier to see. So this is our input here. So we're taking our characters and breaking them up into assigning each one a number and setting that. And then we're doing this one-hot encoding. So again, the network has trouble differentiating between 15 and 16 and 17. They're very close in 18 here. And so it's better if these are encoded with different inputs. So here 16 is, we're given a sequence of 42 letters or numbers that are either 0 or 1, and only one of them will be 1 here. So if this is the 0, first, second, third. So the idea is that maybe this one would be A and this would be B, C. So if one of these is on the one of these letters, and this would be one of the, this might be the letter T, something like that in the alphabet. So only one letter is on at a time, and we're given this sequence of time again. And so this kind of shows our input sequence this doesn't show the whole thing, and it's just showing zeros because the ones are kind of hidden in the middle of this. But this is one example of one long sequence. And then again, the network is going to predict. This is what is actually trained to predict is the next character. So it's saying the next character is this character T. And so that's how we're encoding these characters for input into this network. So this is what we end up with. We end up with sequences 100 characters long. Each part of the sequence is 42 character or 42 digits or zeros and ones, and only one of them will be on marking this. And then we have 142,000 of those that we're training through this network from the Alice in Wonderland text. Okay, here's our network that we're going to try to train here, and then we're going to actually do the training. But again, this is where you can play with the epochs and how many things. Again, if we're feeding 142,000 sequences in here, this might take a while to run here. So again, this is going to take a while. And so right now I'm training it through the whole text 5 times. It'd be better if I did longer, but again, it's estimating. I think this is going to take maybe an hour to train here for just one epoch. So this might take 5 hours to train. So you're going to have to set this up and let it run here. Once it runs, you are going to run. We have this function here to define the network, and then we're going to generate 3 sets of text with this 25 characters long. So let this run, and then it should generate this text. And then your job is to look at this text and see if it's any good. Is it able to generate text that is anywhere meaningful? Is it just putting out garbage, or is it generating text that is meaningful? Do some qualitative analysis on that. Now for the write-up here, I was noticing the write-ups have been a little shorter than I've been wanting. So to help with that, I'm moving the write-ups to a separate Google Doc. I thought people might be more likely to type more in a Google Doc rather than this. So we're going to try this out. So you've got this Google Doc that we're going to look at. And so here's your task, and then what you have to write up here in your write-up, and in here is task 2, and so all of the write-ups here. So you can just make a copy of this and share it with me. And I want you to submit both of these, the project and the write-up, when you turn these things in. Okay, so that was the first task. For the second task, it's related to this. You're going to go back and try to make one modification. So your job is to hypothesize one change that would improve this network performance. So would using more epochs help or less? Would changing the network configuration help? What do you think would be a better help? We looked at sequence size. Would reducing the sequence size or increasing the sequence size help? Would switching this from long short-term memories to simple recurrent networks help? Pick one change, make that change to the network here. One small change, and then rerun this and see if it does improve it or not. So see if your hypothesis is correct, and you're going to write that up. So that's task 2. For task 3, we're going to look at word encodings rather than character encodings. Looking at one character at a time is hard when then you want to generate whole documents. So here we're going to do it word encodings, but word encodings present their own challenges. So similar to before, we're reading in our network, our data here. Now we're using this tokenizer, and this is going to look through all the words and assign each word a number. So rather than each character a number, we're going to assign each word a number. Now, there might be a lot of words in our text. So one of the things we have to do is set the maximum number of words. So right now I'm going to set that to 2,000. And we'll see that. Now, one thing to watch is your RAM usage here. This can fill up all of your memory here and crash your network. Also, if you're using Jupyter notebooks on your own computer, you don't have this display, but your system will crash in your little console display. You'll see a memory error come up. So be aware that this will be an issue. So we set the number of network words that we want to use in our network to some maximum here. That we can look. We display some information. So here's an example of the raw text that's in our network. Here's Alice in Wonderland, Down the Rabbit Hole, Alice Goes. And again, now we're assigning each word a different number. So the is assigned the 1, and is assigned 3, to a, she 6, even the single quote is assigned a 2 here. So and then we end up with almost 27,000 words in our text. So that's how many tokens are in our text. And here's an example of what we're training the network on. So we're just giving it a sequence of tokens here. So chapter is assigned number 315, I is assigned 14, down is assigned 36, the is assigned, well, we already know, the is assigned 1 here. So each, this is the input into our network, is these tokens here. This also shows you the frequency. So down appears 102 times, the appears 1,600 times. There are 2,854 unique words in here. So if we wanted to actually do all the words, we could set this up to that. But this is just going to ignore the least frequent words here. And again, if you use some of the larger texts, you can decide how many words to use later on, but initially set this keep this to 2,000, because again, we have to watch our RAM usage here. Then we're going to do this one-hot encoding. So every word is going to be assigned a vector, and we're going to break this up into sequences. So what we end up with is a sequence of 2,000 zeros and ones here. So there are 2,000 and only one of these on. So this is all 2,000 words, as each input node is assigned a separate word. There's 2,000 inputs and only one of them is on at a time. And then same with the output, we're predicting one. There's 2,000 possible combinations. We're only going to turn one word on as the output. And then we're going to send it sequences here. We're keeping the sequence size relatively small so we don't run out of memory here. So the network's going to see the last 10 words and then predict what the next word is for this. So that's what it's trying to do here. And then the rest of this is pretty well similar stuff. We set up our network, we train the network here. Training should be faster here. We can do more epochs because, again, rather than 100,000 letters, we're training it on 20,000 words or so. And so training should be a lot faster here. And then we're going to have it generate some words here that you can look. And so your idea is to analyze. What we do is we generate, or give it random sequences and have it try to generate the rest of that sequence. So these are the generated word sequence, 3 sample generated word sequences. So your job is to qualitatively analyze those, and then you make some hypothesis on in task 4, how you could change that and improve the network size. Maybe include all the words in the sequence, or longer sequence size, change the type or the size of the network, change the dropout, pick one hypothesis, what you think could improve the network, and modify it and write up that. Last thing we want to do is look at encoder-decoder networks. Your job is to read one of these articles and kind of summarize that. Encoder-decoder networks here, our networks basically are taking one character at a time and trying to generate a prediction for the next word. Encoder-decoder sequences or networks look at a sequence of words, encode them into a a representation, an internal representation of that word or something like that, and then given an internal representation, decode them into a word again. One of the problems we have here, so we only have 2,000 words here, but if we're doing real word recognition, we're likely to have vocabulary, 20,000 inputs. And so working with inputs of 20,000 strings 20,000 long, again, because we do this one-shot encoding where we have a separate input for each word, and that doesn't work for larger vocabularies. And so we need some way to encode words. So we give a word and make some internal representation that's not 2,000 or 20,000 characters long. And so encoder decoder things will take a word and encode it into an internal representation, which can then be decoded into the word itself. So you can read up on those. Encoder decoder networks are also used for images. You can encode images and decode them. And we'll look at that hopefully in the next unit.